Here we have an inclined plane with a cart on it. The cart is being held back by a couple of magnet stoppers, and there's a couple of forces acting upon this inclined plane. Firstly, we have the force of gravity acting down. We have the normal force acting perpendicular to the plane, and we have a force acting parallel to the plane by any frictional forces and, of course, the force that's caused by the stoppers or magnets. We can replace those forces with some strings, and we should be able to take the inclined plane right out of the way. To do that, we have our 3, 4, 5 triangle, 37-degree angle. The force of gravity acting down is weight, and then of course there's an opposing force of weight acting up. That's really just a vector addition of F1 and F2. F1 being the normal force, F2 being the opposing force along the plane. For F1, we have the cosine of 37 degrees times the weight of the cart is going to be F1 because F1 is the adjacent side. For F2, we're going to use sine because F2 is the opposite side of the similar triangle using theta. The mass of the cart is 0.809 kilograms. Again, our angle is 37 degrees. And when we want to find the masses necessary to maintain equilibrium, for M1, we're going to have 0.65 kilograms, while for M2, we're going to have 0.50 kilograms. Gravity will cancel out. And once we place those respective masses, we should have equilibrium. Let me show you over here what that looks like. You can see that on the right we have 0.65 kilograms. On the left we have 0.5 kilograms. And if I pull this out, you can see that we still have the same equilibrium maintained. I can give a pull on one of the masses, it'll wiggle around a bit, give a bit of a tug on the cart itself, and it will go back to the same equilibrium point each time. And I can show that by putting our inclined plane right back in the same spot with our cart. And here we have our equilibrium forces with either an inclined plane or just a couple of strings.